Okay, so let's start with number one. It didn't say in the directions. I meant to say find the area here. So I think our natural tendency is to do top minus bottom, which is perfectly fine. But I'm going to approach this both ways. I'll do top minus bottom, and I'll do right minus left. With top minus bottom, we're going to have to rely on two separate integrals. The reason why is because we have two different top functions. All right, so if I graph, graph. If I draw vertical rectangles, I'm going to see that they're, depending on where I draw the rectangle, there's going to be a different top function. Or the top of the rectangle is hitting a different graph, depending on the region, right? So we see that, to the left of this intersection is going to be the natural log graph. To the right of the intersection is going to be the linear graph. So top minus bottom is fine, but we're going to have to rely on two separate integrals. But if we did right minus left, then all we need will be one integral, but that would require us to rewrite the equation. But if there was a choice on the test, then you can choose either one, and I'm not gonna ask you to do it both ways, so you can have a choice. But I do want to work through it both ways, just so that we feel more comfortable kind of going back and forth if there's some, if you would like to. Okay, so first thing I like to do is find the bounds, right? Find all these intersections. That's part of my problem. So I'm going to take that natural log of x minus 3 and see where that x-intercept is. Find that linear function and the intersection with the x-axis, and then also find the intersection between the two graphs. Okay. I like to start with zoom 6, just so I can get my bearings down here. So it looks like it's extending way past beyond what I can see here. I can zoom out, but I can also just ask the window to show me a little bit more further to the right. So if you go to window, you can adjust that. X-min, X-max will tell you how far left, how far right the graph's going to go. I want the graph to go further right, so I can just push this X-max, just choose a larger number here, choose 30, for instance, graph again. Okay, so we see x-intercept there. I want to push it out even further, so I can just make sure I can clearly see. All right, so I'm going to find my x-intercept first. So if I do second trace 0, so I'm going to choose a point to the left of the x-intercept, hit enter, choose a point to the right of the x-intercept, hit enter. 4. Okay. So I know that my x value is 4 there. Second trace 0 again. This time I'm going to scroll over to the other boundary here. Enter. Go to the other side of the x-intercept, hit enter again. It's going to find that 0 for us, 28. Now I want to find the intersection between the two curves. Do second trace, intersect. First curve, second curve. You don't have to make sure you're not right on the intersection, that you're close to the intersection so that you can give room for the calculator to find it. And it says guess question mark, hit enter a third time. I'm going to find that intersection. It should say intersection. I'm going to go ahead and write both the x and y values down. And if you want to do top minus bottom, all you need is the x value. But if we want to do right minus left, then we would need the y value.
Did you find that point without having to put it in the calculator, or did it just?
You can do a trace, but it won't be as accurate. Yeah. So let me know if you have any. Do you have trouble?
I have a different calculator and I haven't figured out how to grab it like that.
Oh, okay. We can borrow one of mine. Go over that with you if you want to. Okay. So we need two separate integrals, right? One top minus bottom for the curve and the x-axis, and I need another integral between the linear graph and the x-axis. So I'm going to do top minus bottom for this first method. So I'm going to go from 4 to 17. The top of my rectangle is touching the natural log graph. Minus, okay, top minus bottom. The bottom of my rectangle is touching the 0. Okay, that will only give me a portion of the region. I still want the other portion with the linear graph. So that's the integral from 17.346 to 28. Top minus bottom. Okay. Go to math 9. Put everything in. Put this in 7 minus 1/4 x between 17.346 and 28.
Is there a packet for the winner again?
It's in your packet. You have that packet?
Yeah.
Okay. Page 11 through 13. Okay. Any questions with attempting this from a top minus bottom perspective? Find the intersection, find the x-intercept. Let me know if you have any questions on how to find those on your calculator. Okay, I want to try to do this from a right minus left perspective as well. So I'm going to redraw the graph. If I do right minus left, the tedious thing is you're going to have to rewrite the equations. But in this case, the good thing is you only need one integral because if you see that left endpoint of any rectangle that you draw is only going to hit the same graph. Any right endpoint of any rectangle that you draw in this region is only going to hit the other graph. Right? So all we need is one consistent one integral. Okay, but to rewrite the equations here, I need to the 7 minus 1/4 x. I'll have to kind of rearrange it and try to get that x by itself. So I would do 7 minus y is equal to 1/4 x. Multiply everything through by 4 to get that x by itself. So I get 28 minus 4y is equal to x. Okay, so this is the linear graph. It refers to the same graph. It's just rewritten in a different form to allow for right minus left to work. For the curve, my equation is natural log of x minus 3 is equal to y. But the variable is not solved for the correct variable here. So we're going to raise both sides with e as the base. E natural log goes away. I'm left with x minus 3 is equal to e to the y. Solve for x. X is equal to 3 plus e to the y. Okay, so this is the left graph, and this is the graph on the right. Okay. The balance is actually a little bit easier because if you stack all these horizontal rectangles, the lowest it's going to go is 0, but the highest it's going to go is this y value, this 2.663. Okay, so area equals depth integral from lowest y value to highest y value, 0 to 2.663. Right minus left, so we pick out the right endpoint of the rectangle is touching the linear, minus the left endpoint, which is touching the curve. I put all this in the calculator, just the only adjustment in the calculator is that you have to make sure you use X variable. So don't try to force it into a different variable. The calculator is not going to like that. So same answer, 39.053. 052. Any questions with one? Okay, number 2. Given the region enclosed by natural log of x plus 6, y equals -3, and x equals 5. Find the volume generated when the enclosed region is revolved about the line x equals, y equals -4. So this line is y equals -3, so y equals -4 is going to be below it. There's obviously a gap. That rotation is going to have to be washer method. And we're going to have to draw 2 radius, one that extends from the axis to the furthest boundary that we see. And by the way, the x and y axis are not boundaries. They're just there to help give you some perspective as to where the graph is. Okay. And then from the axis to the closer boundary, that's your little r. We're going to rotate this around. This axis is going to look like a ring-shaped figure with a hole in the middle. All right, next up, we need to find the bounds. We want to find the furthest left to the furthest right. Now, the furthest left is just going to be wherever the natural log graph intersects with the y equals -3. The right end point should be easy. That's just going to be this vertical line 5. So whatever this intersection is to 5. You can always start with zoom 6 just to see where how the graph looks. I think for some calculators, it doesn't look like it's connecting. So if that's the case, you may need to do zoom box, and actually zoom in on that region. I saw that for some calculators where it doesn't look like it's connecting, but that's partially because it kind of turns into a vertical asymptote near that region, so it kind of disappears. So you kind of have to zoom in a little bit. Okay, so now I can look for that intersection. If I do second trace intersect, because I want to find the intersection between that horizontal line and that curve. So my first curve, I'm going to choose the natural log. Second curve, I'm going to choose the line. Enter again, finds that intersection for you. I'll go ahead and write both the order pairs down in case I would need it later. All right, let's build our radius. Big R, top minus bottom. The top of big radius is sitting on the curve. Minus bottom. The bottom of my big radius is sitting on the -3. So careful, we got to keep track of both negatives here. Okay. Clean this up a little bit here. All right, understand that this x plus 6 is inside the natural log. We can't make this natural log of x plus 9, right? The best we can do is put them next to each other, but there's no like terms for us to combine here. Yeah.
Is it the A or -4?
Oh, sorry. -4. My bad. Thank you. Okay, now to the little radius. Top minus bottom. The top of little radius is sitting at the -3, and the bottom is sitting at the -4. So we subtract those two. Right. Washer method. So big R squared minus little radius squared. Our bounds is from -5.95 to 5. Whenever you're doing your bounds, you're only caring about the shaded region. Axis of revolution, no matter how far away it is, it's not going to have any input as to what the bounds are. So your bounds is just restricted to the shaded region. Don't let the axis kind of throw you off and feel like you got to go a little further because of the axis. I'm just gonna put the big R under Y3, so I don't have to type in as much. Or involve as many parentheses, so let Y3 be my R, big R. At 9. So there's my big R squared minus little radius squared dx. Okay, this is rotation around an axis. This is circle related, so there's going to be that pi involved in our answer, and our this is volume calculation, so units cubed. Okay, number 2, part B, next page, page 12. Same shaded region, but now we're rotating around the line x equals 5. Going to be right up against the edge of my diagram. So this is a right minus left, but it is also just going to be a disk method. There's no gap between the axis and the shaded region. Um, well, I know the right endpoint is this line x equals 5. The left endpoint is the curve, and the curve requires me to rewrite the equation here. But I do want to solve for x. Raise both sides. E is the base. Okay, right minus left, R of y. All we need is one radius. Again, there's no gap between the axis and the shaded region. It's up against a flat surface. No washer method. All we need is one big radius. Okay. So the right endpoint is sitting at this vertical line, x equals 5. The left endpoint is sitting at the curve, this e to the y minus 6, so minus parentheses e to the y minus 6. Here, I can combine some like terms. If I drop the parentheses, the 5 and 6 can combine. Okay, so imagine stacking these horizontal rectangles from the lowest to the highest y value. The lowest y value is easy to spot. This is going to be this y equals -3. Now the highest y value is going to be this intersection between the curve and x equals 5. Now you're not going to be able to graph this vertical line and the curve and find that intersection. There's an easy way to do this, and that is just plugging 5 into the curve, right? Because you know that this, we're talking about an x value of 5, on the curve. So if I just plug 5 in for natural log of x plus 6, I can get that y value. Right. Imagine you're just trying to find a y value on a curve, which is plugging the x. That's natural log of 11. You can get a decimal version of that. .397. 398, either one's fine. All right, so now we've identified the highest y value of the shaded region. We've identified the lowest y value. Now we can put it into this method. Okay, lowest y value, -3, highest y value, 2.397 or 2.398. Big radius squared. Leave the pi out of the calculator. Make sure you replace that y with an x. You'll get that decimal value, attach pi at the end. It's a volume calculation, so units cubed. All right, number 3. We have the curve, the radical function. This is the square root of x plus 6. That's the one on top. E to the x plus 1, that's the exponential function. So that's the one on below. Find the volume of the solid generated when the enclosed region is revolved around the line x equals -6. So let's go ahead and graph these functions first so we can figure out where these intersections are. Okay. Let me do zoom 6 here just so I can get it. Okay, it's a little small. I'm going to do zoom box here. All right, so I want to find this intersection first. Do second trace intersect. Pick a point near your first intersection. Enter. Make sure your cursor is sitting on the other graph. Enter again. It'll find the first intersection for you, -4.982. I'll go ahead and write down both the order pairs. -4.986. Find the other intersection, second trace intersect. Now I'm going to move nearer to the other intersection. .428 or 0.429. Okay, everything I need in terms of the boundary is identified. Okay, now I know that x equals -6 is going to be over here, somewhere over here to the left. Okay, we know that this is nowhere near the, there's no flat surface here. This has got to be a washer method. So I need to draw two radius, one that extends from the axis to the furthest boundary of my shaded region. And then the little r is going to extend to the closer of the two boundaries. All right, so I need to, anytime you see right minus left, you know you got to spend time to rewrite your equations. There's no way around it. Okay, so first I'm going to focus on the exponential function. Okay, so I'm going to solve for x, but to bring that x down, I need natural log on both sides. Sorry, first I need to move that 1 over so I can get that e to the x by itself. Okay, now I have e to the x by itself. I can take natural log on both sides. Natural log b to the x comes down. Natural log b goes away. There's my curve. Or there's my exponential. Rewritten as natural log. Okay. Next I have y equals square root of x plus 6. If I want to solve for x, I can raise both, I can square both sides first. That will allow me to get inside that radical and then solve for x. So that's this curve right there. Okay, and the axis of revolution is x equals -6. Okay, so we need to build two radius here. So big R. We look at the right endpoint of my big radius is sitting on the natural log graph here. So I can identify that first, natural log of y minus 1 minus the left endpoint of my big radius, which is sitting at the -6, so minus a -6, which becomes a +6, right? Moving on to little radius, the right endpoint of little radius is sitting on the radical, which if I rewrite it is y squared minus 6. Left endpoint is sitting at the -6 as well, so little r. Things up to be just that y squared. Okay, so now we can build our volume formula. This is washer method. We need the lowest and highest y values. Perfect, we have those identified. Right, practice entering that in the calculator. you should end up with 26.032. And then attach pi at the end, units cubed. Okay, number 3, same shaded region. Page 13. But now we're moving on to cross section here. So it says enclosed region is the base of a solid. The cross section of solid taken parallel to the y-axis. So make sure you pay attention to the full description here, and don't just assume that, oh, parallel is always going to be one direction and then perpendicular is the other. It's parallel to the y-axis. So y-axis is vertical. Parallel, that means I want to keep the same direction. So still vertical. Okay, so we're going to be building isosceles right triangle with hypotenuse on the base. So triangles that's going to stick out of this page. Right? And so first we're going to build the length of the base, and then we're going to build the area that's of this triangle, and then we'll put integral notation around it to give it that third dimension. Okay, so top minus bottom. Top. That's the nice thing about top minus bottom is we can hold on to these functions. No need to rewrite anything. The top is sitting at the square root. The bottom is sitting at the exponential. Okay. But I do need a set of parentheses here just to ensure that I can distribute that negative through. Don't not forget about that negative. Okay, so the area that we're trying to build is isosceles right triangle with hypotenuse on the base. So it's not 1/2 base squared, it's 1/4 base squared. So once I can get that formula built, and now I'm just going to accumulate these really thin triangles from one end of my region to the other. So I'm just going to put an integral notation around it. And this is in terms of x, so I need x as my bounds as well. So we found those x values from the previous intersection. So negative 4.986, 0.429. Enter all this in your calculator. Still volume, so units cubed. Okay, last one here. Any questions so far? Okay, number 4, given the region enclosed by the function negative x squared plus 4, that's the parabola opening down, the negative 1/2 x plus 2, that's the linear graph with a negative slope. Find the volume revolved around the line y equals 4. Okay, it's going to be this horizontal line up here. It's going to touch the graph, but it's not up against a flat surface, so there's all this gap that's still going to exist, so this is going to be a washer method. Right? But the nice thing is it's top minus bottom, so no need to rewrite our equations. So from the axis, you're going to extend to the furthest boundary. That's going to be your big R. From the axis, you're going to extend to the closer of the two boundaries. That's the curve. That's going to be little r, shorter. We spend time entering this into the calculator, zoom in, find those intersections. We're going to need those intersections. I'll do zoom box to. I don't think I need to. Just want to get a bigger picture to work with. Okay, second trace, intersect. Negative 1.186, comma 2.593. Okay, 1.686, comma 1.157 or 1.156. This top minus bottom, so really I only need the x values. Okay, washer method, build my two radius. Top is sitting at the 4, the dotted line, minus the bottom of my big radius is sitting on the line, so minus a parentheses, negative 1/2 x plus 2. Careful, make sure you include the parentheses so you don't forget to distribute that negative through. Right, little radius. Top of the little radius is sitting at the 4. The bottom is sitting on the parabola, the curve. Okay. Washer method. Big radius squared minus little radius squared. Okay. Practice entering that in the calculator. Write down your answer, attach pi at the end of your answer. Units cubed. All right, let me know if you have any individual questions.
So when you do that, and that's a lot, you bring them.
The thing is, we have to that you do that by itself first, then we'll take the national log.
Okay.
So, yes, but that, you got to, plus one is y, so nicely it's first. Otherwise, if I do this, okay, that one is kind of getting in the way, so we really want to move that around.
Yeah, no, I understand.
Now it's clean, now I can do this.
Okay, and that's why the natural laws.
It fits together, right? We don't want to just have like that.
That, yeah.
They don't make sense.
Natural log, exponentials, radicals, and some polynomial. Yeah, it should be a single, like the. Yeah. So, I have to calculate for this. Like, let me show you. Yeah, something I can, I can do all this right here. It's just hard to find that.
Still being straight.
Yeah.
It's appeared, but then when you.
I can do this, I can do my
Oh, yeah. All right.
I think you're too hello. Yes, Zoom 6, it'll give you a starting place to look at. So you Zoom 6, and you scroll down at 6 or what? Yeah. Scroll down, it'll give you a standard info. But you can always go back, you can always change your X minus max to adjust. But let's just say you want to kind of draw a block around this to kind of get a little closer look. Go to where you think you want the upper corner of your block to be. You don't want to pick that once you're going to enter once, and go hit enter until you draw the full block. Hit enter. So now let's say I want to find that intersection between the curve and the line. Yeah, we can do like a second trace. Intersection.
You know, it's intersection.
So it's this first curve, the second, so it's asking that. If you pick graph, there's only text going, but it still wants you to tell it. So you can toggle up and down, so I'm gonna pick my first curve here, lateral velocity, second curve. Move the cursor until it's on that other graph, and enter again. Now it says yes, question mark, hit enter a third time. It's gonna zoom in, it's gonna find that intersection for you.
That's gonna be the intersection between the two graphs.
That's right. But let's say for some reason you want to find the x-intercept, you would do the same thing, second trace, but then you would choose 0. It says left bound, so I'm gonna pick a point to the left of the x-intercept. Pick a point on the other side of the x-intercept. Hit enter. And now the calculator is going to look in between the 2 points to do the guess question mark and enter again. Find that x-intercept. We need to borrow this. I just borrowed it. 2 questions. Square. Yeah, you need a second set of things. Yeah, because this alpha is just there, you get where you get the split out. All right.
Thank you. And then.
But the top choice, so yeah, so you I like those.
Oh my gosh.
And they remember like one.
Second.
Like, it's like we graduate every teams are so.
It's like, okay. Two graphs. So much.
So I keep doing these problems and I'm getting the answer from my calculator to be negative. Is that possible? And then I would just like, they just get rid of the negative sign. Or like,
That's weird. It should be not.
like every time, I'm like, can't figure out what to do. The third one, and it's like the same answers on each, but it's like negative. So I don't know if I'm like using something in backwards or something.
Oh, yeah. Are you doing the big R squared?
Yeah, I just.
Oh, I know where you're from. No, but I figured it.
I just looked at it.
There's like three types, just one in, like what we talked about. I just didn't know if because it was like long here, like, it just like, these are a lot.
Ever do the beach here?
Yes, I did it.
They like it. It's nice and early.
Not really pretty con.
Yeah, we have to post some.
It'll be good.
This news wasn't that bad.
Yeah, no, I just need to do like stuff that we learned like.
Okay, so this is actually the exponential graph.
Oh.
That's the exponential graph. So yes, we make it up. So this not minus one, that's that right here.
Oh,
This minus this, that's actually this.
oh, okay, so technically these should be flipped. Okay.
But if you got those two mixed up, you still get the same answer, you just get a negative.
That's like, yeah, well, this one like just stop if you were doing like this and turning.
Exactly, but because you're subtracting the smaller and then the larger, that's why it's creating that negative.
Well, I know that it's one that's not, but it's one right there. Perfect, thank you so much.
Where is it? Wait, right here.
They always think that.
You plug it, like an intercept on the wire.
For.
You plug it to that. Like it's also. Yeah.
That means like, which means that you have to change everything instead of.
Yeah.
Then you have to just jump your code.
I'm pretty sure you just swap out that stuff.
This year. Because you see.
Okay, so is it different for your?
I just always look at, whatever rectangle or radius or base that I draw. If I see a horizontal base, rectangle or radius, I'm gonna do by myself. I gotta check that. If I see a vertical base, a vertical radius, a vertical rectangle, then I'll do it myself.
Or. Area. Like this one, left. Right, okay, so we reading it like that.
Or I could do top minus bottom. But just be a. Two different intervals, there's a region here, and there's a region there.
And you have to turn that into. Like, what is that? How do you?
That y equals -3 is not going to be a graph for you, it's just gonna be a boundary for you. Because, if you look at y equals -3, let's say this is y equals -3, and you have this graph. That's just gonna, automatically, that's gonna turn to a boundary, it's no longer gonna be, one of your graph that you do y minus left. It's gonna be the lowest y value that you have for your integral, but it's no longer gonna be right minus left.
You don't have to do it.
Exactly right. It will never be a part of your equation that you have to adjust.
Okay.
It'll be a boundary potentially, but it's no longer going to be. Well, that's, I put the X and Y out. One. Oh, that was. I'm not gonna make sure you square. All the way.
Right one. Yeah.
Okay, we need a separate, parentheses. Yeah, square, yeah. We have to, or you need, like, six parentheses around the side. Then you can go on to the problem. There's nothing really graph it, if you look for that intersection, right? You can just plug 5 into this curve, and that will figure that one out. There's no need to graph, plug 5 into this. That's accurate, that will make it 5. It's not big, right? And there's some functions using the.
You're supposed to be rating your degree.
Always rated, always rated. All right, clear your desk, so you can have your calculator